Welcome back to my today's CMF session. To myself, Dr. Sayanti Chatterjee, Associate Professor of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today I will discuss some important topics or some important questions on conductors and capacitors. Already we have gone through this chapter previous also, but today just a quick revision or recap type class where if I missed any point, you can get the points also. So today I will discuss about the first question. What is the demonstrate the capacitance between parallel plate when they are separated by a single dielectric medium? So what is capacitance? We know capacitance is nothing but the C is equal to Q by V. What is Q? The number of charge per unit potential is known as the capacitance. Capacitance means the amount of holding the charge, the capacity for holding the charge. So C is equal to Q by V. Now if we want to see, say this is a dielectric plate. This is one path I can show you. So this is the, what is the capacitance? Capacitance is the ratio of stored electrical energy Q and the voltage across the plate or potential difference between the two plates V. You can see if we connected a voltage source from here to here, the voltage is V and this is a parallel plate capacitor. If the stored charge is Q, then capacitance is equal to, we can write capacitance is equal to C is equal to Q by V. Now you can see this is a parallel plate capacitor whose inside cross-sectional area is A, and the distance between these two parallel plates, there is a dielectric medium whose distance is D, and the dielectric coefficient we are taking at epsilon. Actually, for the free space, we can take the dielectric medium permittivity as the epsilon naught, and its value is 8.854 into 10 to the power minus 12. So we know from our previous equation E is equal to Q by epsilon into A. E equals to Q by epsilon into A. So what is the potential? Potential is how we are getting this. First we have a question how you are getting this. If flux density is D, if there is the charge is inside a parallel plate capacitor, there will be some charge and the charge amount is Q. Now if D is equal to, what is D? D is equal to, we know the flux density, electric flux density is equal to D psi by dA, or cross-sectional area, whatever. So what is D psi? Psi is equal to D into A. Psi is equal to D into A, or we can write D is equal to psi into A. What is D? D is nothing but the psi by A. Now from the Gauss law, we know that the number of charge enclosed is equal to number of electric lines of flux or flux. So number of charge enclosed psi is equal to number of charge Q. So we can write it by Q divided by A. So what is D? D is equal to Q divided by A. Now we also know D is equal to epsilon into E. From the relation of the flux density and E, already we have discussed in my yesterday's class. D is equal to epsilon into E. So E is equal to D by epsilon, and D is equal to, we got Q by epsilon into A. So we got E is equal to epsilon into A. This is the proof of getting E is equal to Q by epsilon into A. So we are writing V is equal to E into D. E into D. Voltage or potential is equal to V is equal to minus E into distance. So here the distance between these two are, we can write as the distance between them is d. So q d by epsilon t. What is capacitance? Capacitance is nothing but the q by v. So we are putting the value q by v, and we will get epsilon A by D. Capacitance is equal to epsilon A by D. What is epsilon? Epsilon is equal to epsilon naught, epsilon R into A by D. What is epsilon naught? The number of epsilon naught, epsilon R, relative permittivity. Epsilon R is the relative permittivity. So next question, derives the Ohm's law in the point form. So Ohm's law, what is Ohm's law? When temperature, pressure and other physical conditions remains constant, that time the current flowing through a conductor is directly proportional to the voltage across them. But this is the Ohm's law in a normal or scalar definitions. Now we are moving to the vector definitions, and we will discuss about the Ohm's law in the point form. So first, before starting, we will discuss under the what is drift velocity. So what is the flow of current? Flow of current is nothing but the flow of electrons. So while we are giving a force to the electrons in any metal, there is some free electrons, and under the electric field the free electrons start moving, and it will give the hit the another ions or atoms. From the atoms again some electrons will come out. So if it is a free electron, it will hit the another atom, and again one or two electrons will come out according to its molecular nature. Against these electrons will hit and some more electrons will come out. As a result, there is a flow of electrons, and the speed of the so this is the electrons. So when in the electric field this free electron starts moving, and after some times it attains a constant velocity. If the field is constant, if the potential is constant, it will get some constant velocity, and this constant velocity is known as the drift velocity. The velocity is known as the drift velocity. So we can write that the Vd, drift velocity, is directly proportional to the intensity, field intensity. If we increase the intensity, the drift velocity will increase. So Vd equals to minus mu into E. Vd is equal to minus mu into E, where mu is the mobility constant. Mu is nothing but the mobility constant. Again, we know J is equal to rho V into Vd. How we can know this? J is nothing but the current density. What is current density? Di by ds. Current per unit area is known as the current. And what is current? Current is nothing but the dq by dt. We know current is nothing but the rate of change of charge. So we can write here dq by dt into ds. D of dq by dt by ds. So we can write it like this. Or we can write, we also know what is charge. Charge is equal to what is dq? dq is equal to rho v into dv. Where dv is, here the v is the volume. What is rho v? Rho v is the volume charge density. What is rho v? Rho v is nothing but the volume charge density. What is the meaning of the volume charge density? Charge per unit area. So dq is equal to rho v into dv. We got the volume charge density. So we can write here d by dt is equal to dq. dq is equal to rho v into dv. dv is the volume by ds. So volume means area into length. And what is dv? This is ds. ds is again the area. So if we cut, we will get d by dt rho v into dl. Rho v into l, not dl, rho v into l, length, because volume is equal to surface area into length. Volume is equal to surface area into length. Or we can write rho v is a constant term, dl by dt. dl by dt means rate of change of length is nothing but the velocity. So from here we can write rho v into vd, the drift velocity. So from here we can get current density J is equal to rho v into dv. So we got the two equation. So if we put the value, we got the rho v is equal to volume charge density as we discussed earlier. So J is equal to, what is J? Rho v, and in the place of Vd we are writing minus mu e. So minus rho v into mu e. So rho v into mu can be written by sigma into E, where sigma is equal to rho v into mu is equal to conductivity of the conductor. So conductivity of the conductor depends on the mobility constant. In what is the conductivity? Conductivity is nothing but the 1 by rho, where rho is the resistivity of the conductor. Resistivity of the conductor. So this is the Ohm's law, and this equation is known as the Ohm's law in the point form. Next, state and derive the expression for equation of continuity. State and derive the expression of continuity. So again, any equation, as we discussed earlier, has two parts. One is the integral form, another one is the point form. Point form is also known as the derivative form. So now we will discuss about the continuity equation in the integral form as well as the point form. So first we will discuss the continuity equation. Continuity equation means when current will flow, how much continuity it will show. We will discuss the continuity equation in the integral form. So first we know Q. First we are assuming is the Q is the charge in a closed surface. Q in a charge in a closed surface, and current I is equal to minus dq by dt, because the current direction is always in the opposite of the current charge direction. So I is equal to dq by dt. And also we know the what is current density. Current density is equal to J di by ds. Di current density, current per unit area or surface area is known as the current density. So what is I? I is nothing but the integration of J dot ds. What is current? Current is nothing but the integration of J dot ds. So I is equal to J dot ds is equal to minus I is equal to J dot ds is equal to minus dq by dt. So this equation is known as the continuity equations in the integral form. So first we are assuming in a conductor there is a charge in a closed surface and current I is equal to minus dq by dt. What is current density? Current density is nothing but the charge per unit area. So what is current? I is equal to integration of J dot ds. So I is equal to integration of J dot ds is equal to minus dq by dt, and this is the continuity equation in the integral form. Now we will discuss about the continuity equations in the point form. What is the continuity equations in the point form? We will also known as it as the divergence theorem. So already we got J dot ds in a closed path. If we want to change it into the volume charge integral, it will be grad J dV, integration of volume integral of grad J dV. This is the divergence theorem. And what is current? Current is, what is the divergence theorem? If we want to integrate A dot ds, it will can be written as the grad dot A dv. If we want to write that A dot dl line integral, it will be grad dot A ds. So also we can write grad dot A dv. So we can change the label of the integration, single integration to double integration to triple integration by using the divergence theorem. So grad dot J dot ds is equal to grad J dv. I is equal to J dot ds, that we already know. And again current is equal to minus dq by dt. So minus dq by dt already we got in the integral equation is equal to J dot ds in a closed path, can be written as the grad dot J dv. What is q? Q is nothing but the rho v dv. I already discussed in the previous slides also. What is q? Q is equal to rho v dv. Rho v is nothing but the volume charge density. What is the meaning of the volume charge density? Charge per unit volume. So Q is equal to, what is Q? Q is equal to volume integration of rho v dv. So if we equate the both side, we will get minus d by dt rho v dv is equal to integration of grad dot J dv. So both side is the dv, so we can remove the both sides, so we can write delta rho v by delta t. Why delta? As the charge is in a three-dimensional, so we can use the delta instead of d. It is better choice. Is equal to grad dot J dv. So both side is dv, so we can write that the grad dot J dv. We can write that the grad dot J is equal to, if we equate grad dot J is equal to delta rho v by delta t. Grad dot J is equal to delta rho v by delta t. And this is the continuity equation in the point form. So we got the continuity equation in the integral form and continuity equation in the point form. Got the continuity. Now we will give one small problem from this chapter. A conductor wire of diameter 1 millimeter and conductivity 5 into 10 to the power 7 ohm per millimeter has 10 to the power 29 free electrons per meter cube. When an electric field of 10 millivolt per meter is applied, calculate the charge density of the free electrons. So what is the meaning of the charge density? Charge per unit volume. Now charge of one electron is minus 1.6 into 10 to the power 29. It is given that the 10 to the power 29 free electrons per meter cube. What is the meaning of per meter cube? Per meter cube means unit volume. So we can write it 10 to the power 29 into 1.6 into 10 to the power minus 19 is equal to 1.6 into 10 to the power 10. And what is the unit of the charge? Coulomb per meter cube. So this is the charge density. What is the next calculation? The current density. Current density we have discussed in the previous slide. J is equal to sigma E. What is sigma? The conductivity is also given as 5 into 10 to the power 7. And what is the electric field? 10 millivolt per meter. So we can write 5 into 10 to the power 7 into 10 into 10 to the power minus 3. So we are getting here 5 into 10 to the power 5 ampere per meter. So we can calculate the total current density. So what is the total current? I is equal to J into S, surface area. But how to get the surface area? S is equal to, surface area is equal to pi R square, and R is given as 1 millimeter. So we can write 3.14 into R is 0.001 square. So 3.14 into 1, 2, 3, 10 to the power minus 6. So what is the current? 5 into 10 to the power 5 into 3.14 into 10 to the power minus 6. So it will come near about 1.6 amps. So this is the, this will come, if we multiply, it will come the value near to this. Next important topic is the boundary conditions between the conductors and free space. This is a very important topic, the boundary conditions between the conductors and free space. I will tell one by one line first. So when the electric flux passes from one medium to another medium, their characteristics change, and the condition existing in the boundary is known as the boundary condition. I am giving one more one more example, that if there is an overhead line, when current passing through the overhead line, the electric flux from one medium to another medium, the characteristics change. We will say from the conductors, if it is aluminium or a copper conductor, it is passing through the air. So air is a dielectric medium and copper is a proper conductor. So the nature of the electric flux passes through it will change, and the condition existing the boundary is known as the boundary conditions. And we will take some assumptions. Field intensity and field density inside a conductor is always 0. We know the general tendency of the charge is to stay on the outer line outside of the conductors. Inside there is no flux of a conductor. So field intensity and flux density inside a conductor is always 0. Charge only appear on the surface. So as I told before also, the charge only appear on the surface of the conductor. The charge density within the conductor, as charge is 0, the charge density is also 0. So we are taking, say this is a overhead lines. I have taken this from the UA Bakshi book. I have taken this from the UA Bakshi book. So this is a conductor, this is a medium, this is the inside medium, this is the outside medium. We are taking the medium. And this is the, if we are just taking this medium from here, the distance is the total distance of the depth we are taking as delta H, and the area, the width we are taking as the delta W. Delta H by 2 in the conductor, and again delta H by 2 is in the air. So this is the condition we are taking. This is the conductor and this is the free space. This is the conductor portion and this is the free space portion. So as I discussed, this is the conductor portion and top is the, now there is the intensity, and intensity is always on the tangential direction. Intensity is always in the tangential direction. E can be dissolved into two parts. One is the tangential part, E tan. In the green line you can check this. This is the E tan, and you can see the normal component E n. The orange one is the E n. E tan is the tangential component and E n is the normal component. If you compare with this diagram, there are two tangential components. you can see there are two tangential component. The AB and CD are the tangential component. BC and AD are the normal component. So you can see the BD is the normal component, AD is the normal component, and AB and CD are the tangential component shown by orange and green color. Actually, the color is not coming properly here. Now you can see. And what is the direction? Then if we start from A point, AB, BC, CD, DA, we are taking this conductor AB, the brown one, BC, blue one, CD, green one, and DA is the yellow one. This is the direction of the EMF. So, and the total EMF, as I discussed, is the summation of the EMFs are 0. So, integration of A to B EDL, B to C EDL, C to D, C to D EDL, A to again D to A. This is D to A. So D to A, so A to B, B to C, C to D, D to A. EDL is equal to 0. Now you can see the inside the field. We know inside the field the flux is 0. So ECD is already 0. As we took the assumption, inside the field is 0. So CD component we can make it 0. So EA to B is equal to 0. B to C is equal to 0. And D to A equals to 0. Now again we are coming back to our old diagram. So you can see from here, this is our E10 and E normal. These are our two components. And you can see now, or I will tell from our previous slides. So again in the case, what is we can write? This BC line, half portion is outside the layer, outside the conductor, and this portion is inside the layer. Similar case into the CD. Half portion D to 1 is inside the conductor and 1 to A is the outside of the conductor. So we can again write A to B E dot DL plus B to C, we can write it B to 2 E DL, because this portion is again inside the conductor, it is 0. CD is already 0 and D to 1 is already 0. So we are taking 1 to A E dot DL, because this portion is already, this total portion is already 0. Our main aim is on this. Our main aim is this portion only. So what is the equation of this portion? A to B, B to 2, 2 to 1, because it is already 0, no need, and 1 to A. So this is our main integration. Now what is 2 to B? 2 to B direction is nothing but the 2 to B is nothing but the delta H by 2, because if the total point is H, if it is the midpoint, delta H by 2, and if this is the H direction, it will be minus delta H by 2. So we can write E dot DL is equal to delta W, DL is equal to delta W. So we can write E into delta W plus E delta H by 2 plus, minus, this is minus E delta H by 2 is equal to 0. So these two will cancel out. We will get E delta W is equal to 0. We will get from the next equation E delta W equals to 0. Now you can see what is E delta W. E delta W means this direction, this is the tangential, because other one is the normal component. We are thinking about the tangential component. So we can write E in tan is equal, if E tan of delta W equals to 0, this is the boundary condition between the conductor and free space. This is the boundary condition between the conductor and free space. Next, define the dipole moment and reduce its expression. What is dipole moment? A dipole results from the displacement of the charge is said to be dielectric, is to be polarized. In a polarized state, the electron cloud is distorted by applying the electric field. In the polarized state, if this is polarized, the electron cloud, if this is an electron cloud, means a lots of electron in one point. If we connect it with the source, it will be the positive charges will be comes in one side, negative charge will go in the another side. So this is called the distorted. If it is a circular nature, it becomes little elongated. Already in details we have discussed my old discussion about the polarization. The distorted charge distribution is equivalent by the principle of superposition to the original distribution plus a dipole whose moment is P is equal to QD. So what is the dipole moment? Dipole moment is equal to P is equal to QD. And we can write, if there are lots of charge, we can write the total moment of this is equal to K equals to 1 to N Q K D K by delta P. For one charge is equal to Q K D K. So for the N number of charge is the summation of Q K D K 1 to N, and we are calculating for per unit volume by delta V. Explain the formation. So formation of dipole in the electrostatic field. An electric dipole is formed when 2 point charges of equal magnitude but opposite signs are separated by a small distance. When an electric field E is applied, the positive charge is displaced from equilibrium position in the direction of E by a force QE, while the negative charge is displaced by the opposite direction F is equal to minus QE. So when both one is in the plus QE, another one is the minus QE, and at that time the dipole moment will be P is equal to Q into D. What is this? If it is a positive charge and if it is a negative charge, the distance between them is, we are taking the distance between them is D, then electric dipole is equal to P equals to QD. So we have already discussed this. The distance traveled by the point charge is defined as dipole moment. The product of charges traveled by is called the, and P is equal to QD, and this line is known as the axis of dipole. This line is known as the axis of dipole. Extract the expression for torque of an electric dipole in an electric field. Now we will discuss about the expression for torque on a dielectric dipole in an electric field. Say this is a dielectric, plus Q and minus Q, two charges are there and they made an angle theta with the origin. The distance between them we have taken as D. So the force experienced of Q1 is equal to F1 is equal to E into Q, and F2 is equal to minus E into Q. Direction of F1 is this, F2 is this, and what is the total force experienced? Total force is 0. But as the both direction will be the different, they will create some oscillation, and this is nothing but the torque. So T is equal to, what is torque? Torque is equal to magnitude on perpendicular distance of the distance between the line of action. So perpendicular, so we have to take the perpendicular distance between the line of action. If this total length is D, we will take it as D by 2. So, or if the distance is R, it is R by 2. So we can write it as, if this from the midpoint we are taking R and R, so what is the total distance between them? Between them is 2R sine theta. So magnitude of the force is E into Q into 2r sin theta, 2eqr sin theta. So we got again q into r is nothing but the dipole moment. Q into r is nothing but the dipole moment. So T is equal to Q into 2r is equal to P. So magnetic potential PE sin theta. So this is the torque of an electric dipole in an electric field. Next question. Illustrate the expression for electric field intensity due to a dipole. So already I have discussed in the dipole moment. Just one quick revision. We have one point P. This is the plus Q charge. So what is the distance? This distance is A, and if this is the point is xy, so this point is x. So what is the distance of this point? This point is x minus A, and this height is y. So this R1 is equal to, what is R1? R1 is nothing but the, what is the V1? V1 is equal to KQ by R1. And what is R1? R1 is nothing but the x minus s square plus y square. X minus s square minus y square. So what is V1? V1 is equal to KQ by square root of x minus s square plus y square. Now if we think about the V2, what is V2? It is minus Q2. So minus KQ by R2. What is the R2? If this point is x, so this is x plus A. From this it is x, so this point to this point distance is x plus A. So what is, we are thinking about this, so x plus A. So what is this? X plus A square plus y2. So what is V2? V2 is equal to minus KQ of square root of x plus a square plus y square. So what is total V? Total V is equal to K by, what is the total V? Total V is equal to KQ plus by x minus a square plus y square minus KQ x plus a whole square plus y square. If r is much greater than 1, we can write x plus a square plus y square as r square plus 2ax. We are making it small, r square, square root of r square plus 2ax. Now we will take this, if the angle is theta, then what is x? X is equal to, if this is r, so what is x? X is equal to r cos theta. We got x is equal to r cos theta and y is equal to r sin theta. So we can write square root of r square of 2ar cos theta. So after substituting this value, we will come kp cos theta r square minus a square cos square theta. So this is my today's discussion of this class, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.